Imagine standing in the Middle East about 14,000 years ago. There are no farms, no bakeries, no fields of neatly arranged wheat, just wild grasses and plants growing across a changing landscape. Their seeds were small and often enclosed in tough outer coverings. Eating them directly was difficult and inefficient, so people had to process them. They harvested seed heads with sharp stone tools, carried them back to camp, and began a surprisingly complicated process. The seeds were stripped, crushed, ground between stones, mixed with water, and eventually exposed to heat. The result was something very different from the grain they started with, a bread-like food, or more accurately, one of the earliest known forms of flatbread. And that creates a fascinating problem. We usually imagine the sequence as simple. Humans invented agriculture. They started growing grain. Then, once they had plenty of grain, they invented bread. But archaeology suggests the timeline was far more complicated. At Subbaya 1, a Natufian site in what is now northeastern Jordan, archaeologists discovered charred fragments of ancient food more than 14,000 years old. Analysis showed that the fragments contained wild cereals and other plants that had been processed, ground, and baked. In other words, people were making bread-like food from wild plants thousands of years before agriculture became established. These were hunter-gatherers. They had no modern fields, no mechanical mills, no domesticated wheat, and yet they had developed a multi-stage method for turning difficult plant material into something far more usable. That discovery changes the question completely. Maybe bread wasn't simply a consequence of agriculture. Maybe the desire for foods like bread was one of the pressures that helped push humans toward agriculture. Once people discovered what happened when wild grain was crushed, hydrated, and cooked, they had a new way to transform difficult-to-eat plants into usable food. But Subbaya wasn't the beginning. Evidence for humans grinding wild grains goes back thousands of years earlier, and the deeper we go, the more surprising the story becomes. If bread existed before farming, then the story has to go back much further. At Ohalo the Told, beside the Sea of Galilee, archaeologists found evidence of plant processing from roughly 23,000 years ago. The site dates to the final stages of the Ice Age. Mammoths still walked across parts of the world. Agriculture was nowhere close to becoming the dominant way humans obtained food. Yet someone at Ohalo 2 was already grinding wild plants. A large grinding stone preserved starch residues from wild cereals, including barley, wheat, and oats. The evidence does not tell us exactly whether those plants became bread, porridge, or some other food, but it establishes something extremely important. Humans already knew how to transform wild grains into a more usable form. And the story reaches even further back. At Grotta Peglici in southern Italy, researchers found grinding equipment associated with wild oats in deposits dating to roughly 32,600 years ago. The evidence suggests the plant material may have been heated before grinding, possibly to make processing easier. Evidence from other Ice Age sites suggests this was not an isolated behavior. Across enormous distances, humans were discovering ways to make wild plant foods easier to process and consume. Why was grinding so important? Because a grain seed protects what is inside. Its valuable starch is enclosed within structures that make intact seeds harder to process and consume efficiently. Grinding changes that, instead of swallowing an intact seed, humans could break it apart and expose the interior. When ground plant material was mixed with water and heated, cooking could transform its texture and make it easier to consume and digest. In simple terms, humans were using technology to unlock food value already contained inside plants. A tiny seed could become flour. Ground grain could then be transformed into portable, easily portioned foods. The invention of bread was therefore not just about taste. It was about turning difficult plant foods into something humans could use more effectively. But turning wild grain into usable food came at a price, and understanding that price helps explain why bread may have mattered enough to influence one of the greatest transformations in human history. A wild grain seed looks insignificant, but biologically it is a fortress. The seed is built by evolution to survive long enough to produce another plant. Its outer layers protect the nutrients inside, while its starch is contained within structures that can make raw grain harder to process and digest efficiently. That created a problem for prehistoric people. Finding grain was one thing. Getting useful energy from it was another. The solution required technology. First, the seed had to be broken apart. Grinding did that. Stone tools fractured the grain and reduced it into a much finer material. Then came water and heat. When combined, the starch could change its structure, producing a softer and more accessible food. What began as a hard, difficult-to-eat seed could become a paste, porridge, or eventually a baked flatbread. Humans weren't simply preparing food. They were changing how easily their bodies could access its nutrients. Cooking and processing effectively outsourced parts part of the digestive work. The fire and the grinding stone began breaking food down before it reached the stomach. For mobile hunter-gatherers, this created an unusual opportunity. Wild grains were not necessarily the easiest foods to collect. Harvesting them could be repetitive. Removing the husks was tedious. Grinding required hours of physical effort. Yet these processed foods had advantages that many fresh foods lacked. They could be dried, stored, carried, and divided into portions. A handful of grain could become a compact source of food that was relatively easy to transport and store. That may help explain why people continued investing enormous amounts of labor into grain processing. At some point, the effort began making sense. And once humans learned that wild grasses could be transformed into reliable food, another possibility emerged. What if people could make the plants they preferred more predictable? What if they didn't have to rely entirely on seasonal availability? What if they could encourage useful plants to grow closer to where they lived? That question leads directly toward one of humanity's greatest turning points. But agriculture may not have begun simply because farming was easier. In some places, familiarity with grain foods may have helped make cultivation worth the effort. For a long time, the story seemed obvious. Humans became farmers. Farmers grew grain, and once grain became abundant, people invented bread. But the archaeological record creates a much stranger possibility. What if the relationship worked in both directions? What if people became increasingly interested in cultivating grain because they already valued the foods they could make from it? The Natufians are central to this question. They lived in the Eastern Mediterranean before agriculture became established, relying on hunting, gathering, and a wide range of wild plant foods. At sites such as Subbaya 1, archaeologists have found evidence of intensive cereal processing alongside other signs of food preparation. That suggests grain processing could involve substantial investment of time and labor. Harvesting wild cereals meant finding suitable plants at the right time. Then came cutting, carrying, dehusking, grinding, mixing, and cooking. That is a remarkable amount of effort for a food that could also be obtained from other wild resources. So why do it? One possibility is that grain-based foods offered something valuable enough to justify the effort. The grain could be stored, and once processed into food, it could be carried and shared. This becomes particularly interesting when archaeologists look at evidence for large gathering. At Göbekli Tepe in southeastern Anatolia, monumental structures were being built before agriculture was fully established across the region. The site also shows evidence of plant processing at scale. Some researchers have proposed that communal feasting may have helped create pressure for more reliable supplies of cereals and other foods. That does not prove that bread directly caused agriculture. Human societies rarely change for a single reason, but it challenges the older idea that farming emerged simply because planting seeds was easier than hunting and gathering. Instead, the transition may have involved a feedback loop. People valued grain foods. They processed more grain. They invested more effort in harvesting and managing useful plants. And over generations, some of those plants began to change under human selection. But turning wild grass into a dependable crop required something even more subtle, an invisible shift that happened slowly as humans repeatedly harvested, managed, and replanted plants with useful characteristics. The first farmers had no modern concept of plant domestication, no genetics, no understanding of heredity, just observation. Some wild grasses were easier to collect than others. Some held their seeds together longer. Some produced larger or more useful grains. And people naturally favored those plants. That simple preference could gradually change a species. Take wild einkorn. In its natural form, the plant has a brittle seed-bearing stem. When the seeds mature, that structure breaks apart, scattering the grains. From the plant's perspective, that's excellent. It spreads its seeds. For humans trying to harvest grain, it's a nightmare. Now imagine early gatherers repeatedly choosing plants whose seed heads stayed intact a little longer. They harvested those plants more often. Some of their seeds were carried, dropped, or eventually replanted near human settlements. The plants with useful harvesting traits became more valuable. Those traits were more likely to be selected again. Generation after generation, tiny differences accumulated. The result was a plant increasingly shaped by human cultivation and less capable of reproducing successfully without human harvesting. This is one of the fundamental processes behind domestication. Research has linked early einkorn domestication to parts of southeastern Anatolia, while other important cereals, including emmer wheat and barley, were domesticated across a broader region of the Fertile Crescent. These weren't sudden inventions. They were long biological relationships developing between people and plants. Humans changed the landscape by favoring particular grasses. The grasses changed in response to that selection, and eventually, wild plants became recognizable as crops. As communities became more dependent on domesticated grain, the need to manage larger and more reliable harvests grew. That encouraged new forms of storage, settlement, labor, and eventually social organization. The humble grain seed was becoming the foundation of a much larger system, and bread was still evolving alongside, because another discovery was about to transform flat, dense bread into something lighter, softer, and completely different. The secret was invisible. Living organisms were already present in the environment, ready to transform a bowl of dough when the right conditions appeared. For much of its early history, bread was probably flat and dense. Ground grain, water, heat, simple, effective, and filling. Over time, people discovered that dough could become lighter and airier when it was allowed to ferment before baking. The exact moment this was first noticed is lost to history. There was no recorded breakthrough, no named inventor of the first risen loaf. But ancient Egypt became one of the great centers of leavened bread production. The process depended on something invisible: yeast. Tiny microorganisms naturally present in the environment could settle into dough and ferment sugars that became available within it. As they broke these down, they released gases such as carbon dioxide. If the dough had the right structure, those gases became trapped inside. The dough expanded, it rose, and when baked, those gas pockets were preserved, creating the light, airy texture associated with leavened bread. But this transformation also depended on another key factor: gluten. Wheat flour contains proteins that, when mixed with water and worked, form an elastic network. That network can stretch and hold the gas produced during fermentation. Instead of collapsing into a dense mass, the dough can expand and retain its shape. During baking, heat sets the structure and transforms the dough into bread. The result was a completely different eating experience: softer, lighter, more porous, and far more versatile. By the New Kingdom, bread making in Egypt had become a highly organized craft. Archaeological evidence points to numerous varieties, including breads flavored with dates, figs, coriander, and honey. Bread was produced at scale, distributed, and deeply embedded in the economic systems of the state. Workers could receive food rations that included bread and beer. Bread had become part of the infrastructure sustaining an entire civilization. And the connection between bread and beer was closer than it first appears. Both relied on grain, water, and fermentation, with yeasts playing an important role in each. But they were not identical systems. Different methods and additional steps shaped each product. Still, the underlying biological principle was shared. Bread and beer were not as separate in the ancient world as we imagine today. Both revealed how fermentation could transform grain into something entirely new, and that discovery would reshape human diets for thousands of years. Once leavened bread became an established part of Egyptian food production, it stopped being treated as just food. Bread became part of everyday economic life. It could be produced in large quantities, distributed to workers, stored for later use, and incorporated into a wider system of goods and rations. By the New Kingdom, Egyptian bakers were producing many different forms of bread. Some were simple loaves, others included ingredients such as dates, figs, coriander, or honey. Different shapes and recipes could serve different purposes, from ordinary meals to offerings and special occasions. Bread had become a craft, and the scale of production could be substantial. Large baking operations could turn significant quantities of grain into food for workers and communities. But bread was not operating alone. It had a close partner. Beer. Both began with grain, both required processing, both depended on water, and both relied on fermentation. The same grain supply could support both food and drink. For workers in ancient Egypt, bread and beer could form an important part of regular rations. This is one reason grain mattered so much to ancient states. A ruler did not merely need fields. They needed systems capable of collecting grain, processing it, storing it, and distributing food. Grain and bread became connected to administration, labor, taxation, and political power. Feeding large populations required organization. Controlling the grain supply could influence who was fed, and that gave political authorities a remarkable source of power. But producing bread at this scale came with a hidden cost. Before mechanized processing, grain depended on enormous amounts of human labor. The grain had to be crushed, the flour had to be prepared, the dough had to be mixed, and someone had to do the grinding again and again. The ancient loaf may look simple when it reaches the table, but behind it was an exhausting machine powered by human bodies, and archaeology has preserved evidence of exactly what that labor did to them. Bread may have been a remarkable source of energy, but getting to that loaf was exhausting. Before powered mills existed, someone had to turn hard grain into flour. The basic tool could be deceptively simple: a large stone surface. A smaller stone held in the hands, and countless repetitive movements. The grain was placed between the stones and crushed again and again until the pieces became fine enough to use. Then the process had to be repeated, day after day, year after year. This was not just tiring work. Over years, that kind of work could leave lasting changes in the human body. Archaeologists studying skeletal remains from early agricultural communities have found evidence of repeated strain associated with prolonged, repetitive physical work, including activities activities such as grinding. At sites such as Abu Huraira, researchers identified skeletal patterns consistent with long-term, physically demanding labor. Some individuals developed changes to the spine and joints. Their bones preserved the history of repetitive labor. And that tells us something important about the early bread economy. The technology may have been simple, but it wasn't free. Every loaf required energy before it could provide energy. Someone had to harvest the grain. Someone had to transport it. Someone had to remove unwanted material. Someone had to grind it. Then the flour had to be mixed and cooked. The work was spread across communities, but much of it was performed by human bodies. This helps explain why improvements in grinding technology mattered so much. A more efficient mill wasn't merely a convenience. It could change how much grain a community could process. It could reduce the time required to produce flour, and it could alter who performed the work. Eventually, people developed rotary grinding systems that replaced much of the back and forth motion of hand grinding. Instead of moving a stone repeatedly across a surface, people could turn one stone against another. The principle was simple, but it represented a major improvement in efficiency. Later animals, flowing water, and other external sources of power could drive increasingly large mills. The human body was gradually removed from the hardest part of the grinding process, and that transition would have enormous consequences. Because once external power could perform the hardest part of bread production, flour could be produced on a scale that ancient hand grinders could never match. The first great revolution in bread was learning how to make grain edible. The next was learning how to make enormous quantities of flour without destroying the people doing the work. One of the biggest changes in bread production wasn't a better recipe. It was finding a way to make something other than a human body do the grinding. The first major improvement was mechanical rotation. Instead of pushing a hand stone repeatedly across a flat surface, people could turn one stone against another. The motion was more continuous. The grinding surface could be larger, and the amount of grain processed could increase dramatically. Animals could provide the power. A donkey or other draft animal could walk in a circle, turning the millstone for hours. That simple change multiplied human productivity. Then came an even more powerful idea. What if moving water could turn the mill? Water mills allowed flowing rivers and streams to provide a sustained source of mechanical energy. The grinding process no longer depended entirely on the strength or endurance of individual workers. By the Roman period, milling technology had become sophisticated enough to operate on a remarkable scale. The Barbegal mill complex in southern France is one of the most impressive examples. Built during the Roman era, it used a series of water wheels to drive multiple milling units. Its estimated capacity was enormous, although archaeological evidence suggests the complex did not operate continuously. That mattered because the Roman world had enormous populations to feed. Bread was not simply something individuals made for themselves. It was part of an organized food system. Grain could be collected through taxation, transported, stored, milled, and distributed. In Rome itself, large numbers of eligible citizens received subsidized or free grain through state-supported systems. Maintaining the grain supply helped authorities manage a large and politically sensitive urban population. When supplies failed, political pressure could rise quickly. Bread, therefore, became tied to power. The later phrase, bread and circuses, captured part of this political reality. Food was not merely nourishment, it could be political policy, and the technology behind it mattered. A government capable of moving and processing huge quantities of grain possessed a powerful logistical advantage. The humble grinding stone had become part of an industrial system long before the modern industrial age. But the Romans didn't just leave behind machines. They left behind something even more extraordinary. A city buried so suddenly that archaeologists can still see remarkable traces of how its bakers worked when everything stopped. In AD 79, something happened at Pompeii that would accidentally preserve a snapshot of ancient bread making for almost 2,000 years. Mount Vesuvius erupted. Ash, pumice, and volcanic debris buried parts of the city, sealing buildings, workshops, and everyday objects beneath the ground. Among them were commercial bakeries. Archaeologists have identified numerous bakeries across Pompeii, some containing remarkably well-preserved equipment. Inside these establishments were large stone mills. Many used animal-powered mills, with draft animals walking in circles to turn the heavy grinding stones and transform grain into flour. There were also substantial ovens designed for baking multiple loaves. The bakery was not simply a place where someone prepared breakfast. It was a specialized business. Grain entered the operation, the mills processed it, the flour became dough, the dough was shaped, and the finished loaves were baked for sale and consumption. The entire process had been organized into a production system, and then the eruption sealed parts of that process beneath the volcanic deposits. Among the discoveries were loaves of Roman bread preserved by the conditions created by the volcanic disaster. One recognizable form is commonly called panis quadratus, a round loaf divided into sections by deep scoring. Imagine holding one of those loaves today. You would be looking at the physical result of a process that began thousands of years earlier with wild grass and a stone grind. The ingredients had changed, the technology had changed, but the fundamental sequence remained surprisingly familiar. Grain, grinding, water, dough, heat, bread. Pompeii therefore gives us something unusual. Most ancient food disappears. Bread is eaten and gone. But here, a disaster preserved the machinery, and in some cases, the food itself. It allows archaeologists to reconstruct not merely what Romans ate, but how a city organized the production of one of its most important foods. And Pompeii reveals another truth. By the Roman period, bread had become so ordinary that a substantial urban economy could grow around producing it. But the Roman loaf was only one version of a much bigger human idea. Across the world, people who had never met one another were transforming completely different plants into remarkably similar foods. The Romans were not the only people to discover that starchy plants could become bread-like foods. They were part of a much larger pattern. Across the world, societies separated by thousands of kilometers developed their own versions of the same basic technology. The ingredients changed, the shapes changed, the cooking methods changed, but the underlying idea remained remarkably consistent. Take a starchy plant. Break it down, add water, apply heat. In Mesoamerica, people transformed maize into tortillas through nixtamalization, cooking the grain in an alkaline solution such as lime, then grinding and cooking the treated maize into a workable dough. In Ethiopia, teff became a major ingredient in injera, a fermented flatbread with its own distinctive preparation and texture. Across South Asia, wheat-based flatbreads, such as chapati and roti, were cooked directly on hot surfaces. In the Middle East, flatbreads such as pita became deeply embedded in regional food traditions. Across the Caucasus and surrounding regions, lavash became another expression of the same basic principle. And in parts of South America, maize was transformed into arepas. These foods are not interchangeable. Their ingredients, fermentation methods, textures, shapes, and cultural meanings can be dramatically different, but they solve a similar technological problem. How do you turn a difficult-to-eat starchy plant into something humans can consume efficiently? That is why bread is often described as a convergent technology. Different populations can arrive at similar solutions, sometimes independently because the underlying biology and physics remain the same. Starchy plants provide concentrated stores of carbohydrates. Grinding makes them easier to work with. Water creates a workable mixture. Heat transforms it. The final product can become portable, shareable, and in some cases easier to store. The remarkable part is not that every culture invented exactly the same bread. They didn't. The remarkable part is that humans repeatedly discovered the same general strategy while using completely different plants and techniques. Bread-like foods, therefore, aren't one recipe. They're a family of solutions to a universal problem, and their influence reached far beyond the kitchen. The importance of these foods became embedded in language, religion, social class, and politics. Words we still use today carry traces of that history. Because once you start looking closely, bread stops being something we simply eat. It becomes embedded in the words we speak, the rituals we practice, and even the political systems that once depended on keeping people fed. Today, bread feels almost effortless. Walk into a supermarket, and there may be dozens of varieties waiting on a shelf. Sliced bread, flatbread, sourdough, whole grain, sweetened loaves, the choices are enormous. But every one of them rests on a chain of discoveries that began long before supermarkets, bakeries, or even agriculture existed. First, humans learned to process wild plants. They discovered that grinding could unlock nutrients hidden inside hard seeds. Then they learned that water and heat could transform those ground materials into usable food. Later, some communities began cultivating the plants they preferred. Over generations, wild grasses became domesticated cereals. Settlements grew. Grain became something that could be harvested, stored, taxed, exchanged, and controlled. Then fermentation changed the bread itself. Dough could rise, a dense mixture could become light and porous. In places such as ancient Egypt, bread became part of organized food production and worker rations. Grinding technology continued to evolve. Handstones gave way to rotary mills. Animals supplied power. Water supplied power. Eventually, machines would take over much of the work entirely, but the story never belonged to one civilization. People across the world independently transformed maize, teff, wheat, and other starchy plants into their own bread-like foods. They developed different ingredients and techniques because they were solving the same underlying problem. How do you turn a plant's stored energy into food that humans can actually use? That is why bread is so much more than a recipe. It represents an accumulation of human knowledge: biology, engineering, agriculture, cooking, trade, labor, and politics. A simple loaf on a modern table carries traces of all of them. The strange part is that we rarely notice. We see bread. Our ancestors saw grain that had to be harvested, ground, mixed, fermented, cooked, and carried through systems of labor fiber that could shape entire societies. The journey from wild grass to modern bread took thousands upon thousands of years. And it wasn't one invention. It was millions of small decisions. One experiment, one improvement, one generation passing knowledge to the next. The next time you tear a piece from a loaf, you're not just eating one of humanity's oldest foods. You're eating the result of a technological journey that began when someone, thousands of years ago, looked at a tiny wild seed and wondered what else it could become.